Okay, thank you. I'm not Feihu Shu. We're going to give a joint talk. That's one of the two things that are particular. It's also this karaoke microphone that I'm using. There's only one microphone. So I'm going to be talking in the beginning of this talk, and then Feihu's going to jump in to talk about the experiment. So I want to begin following Erica's example in recognizing everyone that contributed to this work. We should not forget that science is indeed a team effort. So most of the, everyone does the same mistake. Most of the theory work was done at IQC, experiment by people from the University of Toronto and collaborators from University of British Columbia and University of Hong Kong. So I'm going to be talking about quantum fingerprinting. What is quantum fingerprinting? Anyway, so we consider a very simple model in which we have Alice, Bob, and the referee. Alice and Bob receive an input of n bits, x and y respectively, and they will send a message to the referee who must determine, based on this messages, whether x is equal to y or not. And we allow some small error probability in making this determination. There are some restrictions, so there is only one-way communication from Alice and Bob to the referee, and they are not allowed to have shared randomness. And then the question that we ask, in particular in the context of communication complexity, is the following. So, given two input strings to Alice and Bob, what is the smallest amount of information they must transmit to the referee in order to solve this problem? So in order to allow the referee to distinguish whether the inputs are equal or not. And the reason that we are interested in this protocol and in this model is the following, because we can prove that if Alice and Bob only have access to classical communication, right, then they must transmit at least asymptotically square root of n bits of information to the referee. And we can prove this as a mathematical theorem. This is the scaling that you require. Whereas there exist quantum protocols, in particular this one by Berman et al., that work even using log n qubits of information. Right? And I want to clarify that actually the figure of merit that we're interested in is the dimension of our quantum systems. And in particular, if the systems have dimension n, then we know that they can transmit at most order log n qubits of information. Right? And this is a beautiful result because it proves that there is an exponential separation in the communication complexity between classical and quantum. And what we're interested in doing, and we're going to be demonstrating as a proof of concept experiment in this talk, is to reach this new frontier of research in communication, in quantum communication, to try to demonstrate the separation between classical and quantum in a practical setting. So suppose we want to implement the protocol proposed by Berman et al. So we have to prepare states that look like this. If we want to use qubits, qubit states, then we are in trouble because we can prove that we need these qubit states to be highly entangled. We need to perform complex operations on these qubits, in particular swap tests. Right? And what has happened is that in previous experiments have been limited to only single qubit demonstrations, which effectively defeats the purpose of showing a reduction in the transmitted information. Alternatively, what we could do is say, well, let's use qubits, right? So systems exactly of dimension m, like I'm showing here. And this gets better, but nevertheless, it's very hard to prepare states. For large m, right? For instance, we could use a single photon across m modes, and they can be any type of modes, but it's very hard to do this for large m, and they're very susceptible to losses and imperfections. So again, we're sad because we don't really have the technology to do this. So the fix, and this is a protocol that we proposed a year ago, is to, instead of using a single photon, use a coherent state. And the way these states look are like this, just a tensor product of coherent states in which we modulate the phase according to some rule. So before I tell you what the protocol looks like, where we're using this idea of encoding our states, I'm going to discuss why we're still transmitting exponentially less information in the classical case. So if you consider the case of having a single photon across m modes, right, then we know that there's states, any state of a single photon across m modes spans a Hilbert space of dimension m, and this is mathematically equivalent to a state of order log m qubits. So we can transmit at most log m qubits of information. So if what we do is, instead of having a single photon, we have a coherent state, and then we end up with states that look exactly like this, just a sequence of coherent states, and there's a total mean photon number alpha squared, then in this case we can also prove that the Hilbert space spanned by such states is mathematically equivalent to order mu log m qubits of information. So as long as we keep mu constant, we're also achieving the same exponential separation. And essentially, the idea is that when we restrict the total mean photon number to a small constant that is independent of m, then we're limiting the capability of these systems to transmit information. what ends up happening as well is that we're using states in which the number of modes is linear in the input size, so m is linear in n, right? But the number of photons is small and independent of input size. It depends only on the error probability that we allow. So what does the protocol look like? So what Alice and Bob do is the following, and this is, there's some improvements made from the original protocol that we had. They get an input x, Alice and Bob, they apply an error correcting code, and this error correcting code must have the property of a constant minimum distance. What this means is that as long as x is different than y, then the corresponding code words will differ in at least a guaranteed fraction of the positions. In our experiment, 22%, right? And what they do, they send a sequence of coherent states, and for the referee, the only thing he has to do is interfere them pairwise on a beam splitter and check for clicks in detector D1. And they do is they modulate the phase of these coherent states to be either plus or minus 1, depending on the ith bit of the code word that they produced. So why does this help? We already established that the information that we're transmitting is exponentially smaller than in the classical case. But why does this allow the referee to determine whether the inputs x and y are different or not? Well, let's look at the way these coherent states interfere. So if the phases are equal, what was going to happen is that there's going to be destructive interference in the output of this detector. So in the ideal case, we never expect to see clicks. However, if the phases are different, then we get the opposite effect, in which they interfere constructively in this output, right? And they may or may not click, and the probability is given by the photon statistics of the coherent state, but that's something that we can control by choosing this parameter alpha. So what ends up happening in our protocol is that there's going to be some probability distribution for the number of clicks that we observe when x is equal to y. And if you remember, when x is equal to y, all the phases are going to be equal, like happens here, right? So the only reason we'll ever see clicks in detector D1 is due to noise, like dark counts or because the interference isn't perfect. So this just gives us a background. Whereas if x is different than y, we know that 22% of these pulses are going to have different phases, so we expect to see more clicks. So we're going to get a different distribution in which the mean number of clicks that we expect is going to be larger than in the case where x is equal to y. And in fact, we can control this mean number of clicks by choosing a larger mu. And what the referee does, just simply sets a threshold value, for instance, some number like here. And if you see a larger number of clicks, you'll conclude they're different. And if you see a smaller, you conclude that they are equal, the inputs. And we can choose the error probability and distinguishing the distributions to be any epsilon, right? And so this is a protocol that is practical, as you'll see, transmits less information in the classical case, and actually does what it's supposed to do, right? And so now I'm just going to let Feihu tell you about how we demonstrate this in an experiment.
Okay, so next I will discuss how we demonstrate the protocol in experiment. So the experiment was done at Toronto. Currently I work with Jeff Shapiro and Franco Wang at MIT. So I knew the protocol in early 2014 from a talk by Norbert Lukinghaus. I think Norbert is around. It was a very great talk. After talk, I thought, can we do the protocol in experiment? Then I found the following challenges. First, the protocol have a very strict requirement for the devices, like the detector requires a 50 Hertz dark count. And also, it requires to have a stable interference for very weak coherent state in the order of 10 to the power -5. We know this number is already very low than the normal QKD operations. Third, we need this interference for very large number of pulses. So with this challenge, we're asking, can we relax the requirement and demonstrate the protocol with commercial devices? So the answer is yes. Here's our solutions. First, we design a better error correction code to relax the requirement. To relax the requirement for the devices. And then we use a modified commercial plug-and-play QKD system to demonstrate the quantum fingerprinting protocol. So our error correction code, we use the random linear code. This code has quasi-linear encoding complexity. And in conventional coding theory, we know this kind of code are easy to encode, but very hard to decode. But the good news for our protocol is decoding is not required in quantum fingerprinting. So random linear code is a perfect match for our protocol. So with this code, we have these three advantages. First, we can approach the JV bond which is the fundamental limit between minimum distance and the rate. So for comparison, we have a 3-time improvement compared to previous code called just-in-code. The price to pay is we have a very small failure probability, the epsilon small failure probability. Most importantly, this can relax the devices for the protocol. For example, it can relax the dark count from 50 Hertz to 5 kilohertz. So with this code, we can use the commercial device to do the demonstration. So next we talk about the experimental setup. We use the commercial plug-and-play system manufactured by ID Quantic. And the reason we choose this system because this IDQ system can provide a very good interference for weak responses. So let's talk about the setup. The pulse is generated from the referee, and then the pulse passes through a Mach center interferometer. And the long arm is Bob set. The pulse will split into 2 pulses, this orange one and this blue one. For these 2 pulses, they pass through a 5-kilometer fiber. Finally, they will arrive at Alice. So for the orange pulse, it passes directly go to Alice, and then it reflects back from this Faraday mirror. Because this Faraday mirror, it will be shift the polarization to the orthogonal one. And then the pulse will pass through the long arm. Once the pulse passes through the long arm, Bob used the code word EY to encode this orange pulse. For this blue pulse, it will directly go to Alice. Once it's come to Alice, Alice will use the code word EX to encode the blue pulse. In the end, both pulses reflect back and interfere at this beam splitter. We use 2 single photon detectors and time correlator to check the interference results. So basically, this interference will exactly as discussed in previous slides by Juan. Finally, I want to emphasize these red devices indicate our modifications on top of our original system. So why we do these modifications? First, the initial commercial system, like Clavis 2, have relatively low efficiency and higher dark count. Second, commercial system does not normally allow external phase modulations. Third, the low mean photon number is already outside of the normal QKD operation, which is in the order of 0.1 photon per pulse. So here I will talk about our modifications. First, we replace the detector with 2 external free-running detectors. It's still from ID Quantic, it's IDQ 220, and it has about 20% efficiency and 2 kilohertz dark count, which exactly falls in our numerical simulation. And the second modification is we use 2 external function generators to perform the phase modulation according to the code words. Finally, we use a variable optical attenuator to highly attenuate weak responses. This is our modifications, and to make the system work, we also need precise synchronization, calibration, and polarization control. So in the end, we can transmit about 100 megabits over 5 kilometer fiber with very good visibility, about 99%. So next shows our real experimental setup. This is the box of Alice. This is the box of Bob. This is the referee part. And with this system, we come to our experimental results. We define the quantum advantage as the ratio of classical transmitted information over quantum transmitted information. This is a plot. X is the input size. Y is the transmitted information. And this blue area shows no advantage of quantum fingerprinting protocol. So we found for small input size, indeed, we didn't see any improvement of quantum protocol. And for larger input size, we clearly beat the classical protocol. So to give you an example, for a message up to 100 megabits, which is this data point, the information transmitted is about 66% lower than the best known classical protocol. So then we come to the end of the talk. In summary, we propose a practical current state protocol, and we design a new error correction. We design a new decoding rule and also perform the simulations to consider imperfections. And also we use a new error correction code to relax the requirement for devices. And finally, we construct the system to do the demonstration. The key message is we perform the first proof of concept quantum fingerprinting protocol that transmits less information than the best known protocol. So thank you very much for your attention.
Thank you. Now the session is open to questions and comments, please.
If I understood from the first part, one of the interests of this is that we get provable advantage of log n quantum versus n classical. So this provable advantage is great in the theory. In practice here, you're talking about in your experiment, 66% better than the best known classical protocol. Why can't you do some? Why can't you prove it 60% better than anything classically possible?
It's a very good question. In fact, for this hello. Yeah, there exists a lower bound. There exists a lower bound as well that we can try to beat, but it's much more challenging. So the asymptotics are beautiful, but we have to do experiments for fixed n, and then for fixed n there's going to be some values of how much we're transmitting that depends on things like imperfections. But obviously something that we're interested in doing and that we are in fact pursuing is it was a proof of concept experiment, but there are direct improvements that can be made, and the goal eventually will be to actually perform the experiment in a regime that classically can prove that it's impossible to be that regime. So it's future goal.
I just add a little bit. So we do some calculation to see whether we can beat all the known protocol over the proven lower bound. We found the major limitation is the dark count of our detectors. So in future, if we have a detector with like a few hertz dark count, we found with the same setup, we can still beat the proven lower bound. So that's why it's mainly limited by the detectors in our system.
So is this best known classical protocol the best known deterministic, or does it also include probabilistic protocols?
So it's a probabilistic protocol. Yes. Just behind you, questions.
Oh, this is a matter of terminology. You shouldn't use hertz to measure the frequency of dark counts. The proper SI unit for irregular events is the becquerel, named after the discoverer of radioactivity.
Okay, I agree.
Duly noted.
Thanks. So when you were comparing the classical and the quantum protocol, now you're talking about the ratio of information instead of communication, which is the right thing to say. On the other hand, when we're trying to talk about information, then the idea is that Alice and Bob want to privately let the referee privately compute the things. They don't want to reveal a lot of information about their inputs. However, in your experiment, it's actually the referee who creates the pulses and stuff. So the referee can get much more information if you're really wanting to count the information. If you're counting communication, then there is a different problem, and we know it. But with information, you need to be careful that, it's Alice and Bob, the ones who actually send the information to the referee, not the referee that can start the pulses and then get more information, right?
So in the setup, the referee, when sending the states, doesn't get any information about what Alice and Bob are doing. So they do it privately in how they encode the phases of the states. That's one thing. The other one is that when we are talking about transmitted information, we are not talking about how much information about the inputs is being revealed. So essentially, and I tried to make this clear in the beginning of the talk, the figure of merit is really the dimension of the states that we're using. And then we know that the dimension of the states can bound any information you can transmit about anything whatsoever using those states. So it's not information about X and Y, and it's not them trying to hide something from the referee. That is actually something we're very interested in studying in that terminology in the future. But when we talk about transmitted information, we're really talking about something that we can bound from the dimension of the states that we're using, which is the relevant figure of merit.
Any other short questions?
So I just have a question concerning the classical communication complexity. So you mentioned it's order n. So this assumes independent Alice and Bob, and also does it really assume no errors?
So the lower bound for the classical case is square root of n, first of all, and so it's a protocol that can still err. It's actually one-sided error is the protocols that are being just the best known that it's found in the literature, right? And we are making a comparison in which that protocol is realized perfectly as well, right? So there's an error in the sense that there's a probability of not correctly determining whether the inputs are equal or not, but not errors in the sense of imperfections in the deployment, right? So we assume that we're comparing against a perfect implementation of a classical protocol.
Okay, so please make it short, please.
I was just wondering if, so basically your Hilbert space was mu times log m, right? So if
Correct.
coherent states are weak, then you have a small Hilbert space. But if they are very strong, then of course it starts to grow. But then if the coherent states are too weak, I assume the probability of success takes a hit in some way, or is that not the case?
So what you want is to have mu to be independent of the number of pulses that you're sending. So in fact, how weak the coherent states are depends on the input size, because the number of pulses that you have depends on the input size itself. However, the error probability depends only on the total mean photon number. Right? The only reason that you might run into trouble eventually is that if the probability of obtaining a click due to your signals is comparable or even lower than the probability of getting a dark click in the detector, then you are limited. And that's why Feihu was saying that that's actually one of the limits in trying to beat the lower bound in the classical case. It's that you need detectors with really low dark counts so that you can go for very small total mean photon numbers and hence very, very weak coherent pulses, right? In our experiment, they were already 10 to the -5 mean photon numbers per pulse.
Oh, see, so there are no dark lux, then there's always a regime of coherent state strengths that you can always beat the classical.
Yes, correct.
Okay, thanks.
Okay, I think it's time now, so let's thank the two speakers again.